Okay, so we're going to go through how to solve an integral using U substitution. U substitution is basically backwards chain rule. So if you think about how you take the derivative and use chain rule, U substitution allows us to undo the chain rule. And it gives us a process rather than guessing and checking. So I'm going to quickly go through the steps here. So the first thing you always need to do is figure out what to make U. And the easiest way to figure that out, because sometimes you're going to have to guess and you're going to have to say, okay, I'll try U equals this. And sometimes that U doesn't work and you'll have to go back and choose a different U. But usually the way to figure out what U should be is it's an equation whose derivative is being multiplied inside the integral. So again, sometimes you pick a U, it might be wrong, that's okay. You can go back and pick a new U and try again. Find the derivative of your U equation and solve for your du. Then you're going to rewrite the original integral in terms of U only. So this is going to be big on like, your final or the AP exam, is the fact that you do need to rewrite your integral in terms of U. So get in the habit of doing this. Don't just use the guess and check method and say, oh, well, I've always used guess and check and it's always worked. You are going to have to know how to use U substitution. That is a requirement. Then once your integral is rewritten in terms of U, then we'll integrate and solve. So when you're figuring out what U should be, again, sometimes you'll be wrong the first time, but there's only a certain number of functions that you're going to see here. Like here I have 20x, I have e, I have 5x squared. I only have a few different things I'm seeing. I'm seeing an x, I'm seeing an e, I'm seeing 5x squared. So it's not like there's an infinite number of U's to pick, So looking through this, I see an x. Again, I see an e and a 5x squared, and I think, okay, which one of these has its derivative being multiplied? For example, I have e to the 5x squared. Well, the derivative of e to the something is e to the something, but I don't have another e that's being multiplied. I only have one e here. So I don't think that my u is going to equal e to the 5x squared because I'm not multiplying by another e. I've got 5x squared. The derivative of 5x squared is 10x. Now 10x is pretty darn close to 20x. And I can deal with constants. Constants are not a big deal. So if you have 10 turning into 20 or you have 3 turning into 7, it's not hard to multiply by a number and have your constants be equal. So I'm going to let u equal 5x squared because, again, the derivative of 5x squared is 10x. And I can see that 20x can contain a 10x within it. Du is simply the derivative of u, and we're taking the derivative with respect to x. So I'm going to show you this step, this full step, but in the future I probably won't show this step. So du dx is equal to 10x, which means du is equal to 10x dx. So usually I kind of cut straight from that step to this step. I don't show that intermediate step. But just so you understand why du is equal to 10x dx, it's because you're taking the derivative with respect to x on both sides. So I get du equals 10x dx. So right now what I can do is if u is equal to 5x squared, and I have du is equal to 10x dx, well, this is 20x dx. So what can I do to du to make that 20x dx? Well, I can just multiply both sides by 2, right? And then, since 20x dx is equal to 2 du, I can substitute my green underlined portion. I can substitute 20x dx with 2 du. So here's where the substitution part comes into play. I'm going to have the integral, and I'm going to replace the 20x dx with 2 du. And I'm going to move the du to the outside because we like our dx or du to be at the end. So I'm going to replace the 20x dx with 2 du, and then everything else, I still have an e, so the e is not being replaced. It's still got to stay there. But the 5x squared is just u. That's so it's less awkward. So the integral of 20x e to the 5x squared dx can be rewritten as the integral of 2e to the u du, with understanding that u is equal to 5x squared. So again, start by finding u, then find du. If you need to multiply or divide by any constants so that you end up with what you started out with, and then go ahead and do that. So in this case, we had to turn a 10 into a 20, so we multiply both sides by 2. And then make sure you are replacing every single thing. So you're replacing the 20x and the dx with this. The e is staying around, so that's just being replaced by e, but the 5x squared is being replaced by u. And then, well, what's the integral of 2e to the u? So now we're integrating with respect to u. We're not integrating with respect to x. And the antiderivative of 2e to the u is just 2e to the u, right? Because the derivative of e to the u is still e to the u. And this is an indefinite integral, so I do need a plus c. And then I do need to go back and resubstitute what u is equal to. It's 5x squared plus c. And if you want, you can and probably should double check that your answer is correct. If I took the derivative of 2e to the 5x squared, I'd have to use the chain rule. So the derivative of 5x squared is 10x times 2, and then the derivative of e to the something is e to the something. And hey, that is what I started out with. So that's my first example. Let's go through a second one. I've got negative 8 tangent of 3x secant squared of 3x dx. So again, I'm looking for a u whose derivative is being multiplied. I have a tangent, I have a secant squared, so I can think about that. I can think of, that function as either just secant, or I can think about it as secant squared. So I've got a few different choices here. But right off the bat, I'm thinking, okay, well, what's the derivative of tangent? The derivative of tangent is secant squared. So I'm going to let u equal tangent of 3x, because then the derivative is equal to, and we have to use the chain rule here, right? The derivative of tangent of 3x would be 3 secant squared of 3x dx. Okay. So again, I chose u is equal to tangent because I know the derivative of tangent is secant squared, which I see is being multiplied. Okay, now I have a 3 here, but here I have a negative 8. So how do I turn a 3 into a negative 8? Well, I can multiply by negative 8. And I can also divide by 3. And then I get negative 8 secant squared of 3x dx. So if I have negative 8 over 3 du, that is equal to negative 8 secant squared of 3x dx. What that will allow me to do is replace the negative 8 and the secant squared of 3x dx with negative 8/3 du. So let's go ahead and plug that in. So I have negative 8/3 du, which again I like to leave on the outside. And then the tangent of 3x, well, that's just u. Give myself too much space. Tangent of 3x is equal to u, so I can replace that whole tangent with u. So again, make sure everything is being substituted correctly, or everything is in terms of u now, including my du. And then what's the antiderivative of negative 8? Again, it's just a constant, so just pull out the constant if you want, negative 8/3. The antiderivative of u is going to be 1/2 u squared plus c, which is equal to negative 4/3. And what is u? It's tangent. So tangent squared of 3x plus c. So you always want to go back and replace your u's with x's if you have an indefinite integral. Okay, so in this problem, we have an indefinite integral. And I notice a couple of things. First of all, I notice that we have an x squared, and I also notice that it's in the denominator. So one thing I could try to do, I'm going to try a few different things, is I could try to do like 7 times 4 plus x squared to the negative 1. But if I let u equal 4 plus x squared, then du is going to be 2x, and I don't have a 2x in here. So I can't let u be any form of the x squared part. So this is not going to work for me. So a lot of times students will say like, oh, I'll let u equal 4 plus x squared, and then that becomes, 7 times 1 over u, and then, then they like say it's okay, it's ln, right? But you can't actually do that because the derivative of x squared is 2x, and that's nowhere to be seen. So we are going to have to use something else. And what I'd like you to do is you can take out this 7 here if that helps. And you might recognize this, that this looks very similar to this. And this integral is the derivative of tan inverse of x, right? The derivative of tan inverse of x is 1 over 1 plus x squared. So this looks similar. The only difference is we have a 4 here, okay? But we can factor out the 4 as well. So when I do that, I can make this become a 1, because it does have to be a 1 here in order to be inverse tangent. So we can factor out the 4, we're left with 1, but we're going to have to divide that x squared over 4. Okay, because again, 4 times x squared over 4 is x squared. If we're going to factor out a 4, we're going to have to divide x squared by 4 as well. So then that gives us 7/4 times the integral of 1 over 1 plus x squared over 4. Now, x squared over 4 is the same thing as x over 2 squared. Okay, so when you recognize that you have an inverse tangent or inverse sine or inverse secant, and typically you'll get inverse tangents or inverse sine. That's usually what's on the AP exam. But you could also get inverse secant or, cosine, cotangent, cosecant. But what you want to do is make sure that you have a 1 everywhere where you're supposed to have a 1. It's okay if this part changes to something else, because we can use the chain rule on the x part, but we can't use the chain rule on the 1 part. So make sure that you factor things out so that you get 1 over 1 plus, or 1 over the square root of 1 minus, or whatever it is. So now that our 1's match, now I'm going to use u substitution on the x over 2 part, okay? So I let u equal x over 2, which means du is equal to 1/2 dx. So du equals 1/2 dx, so I can multiply both sides by 2. I get 2 du equals dx, okay? So then my integral is going to become 7/4 times the integral of 1 over 1 plus x over 2 becomes u squared. And now you can see that this matches up. And then instead of dx, I replace that with 2 du. So I'm going to pull out a 2 and then multiply by du. And now we can see, let's go ahead and simplify that. That's going to be 7/2. The antiderivative of 1 over 1 plus u squared is tan inverse of u plus c. Don't forget your plus c, because this is an indefinite integral. And then we replace what u is. Tan inverse of x over 2 plus c. All right, so again, if you are looking and you see you can't use like backwards power rule or backwards exponential rule or backwards log or whatever, if you don't see the derivative is in there, it might be something like this. It might be kind of a curveball where it's an arctan or arcsine inverse. Arctan or arcsine derivative. So that's why you want to really know those rules and be able to pull them out when necessary. So again, the 1 needs to be a 1, the 1 needs to be a 1. It's the x part that you're allowed to use u substitution on. Okay, so this next one, this is a very common problem. What's the antiderivative of tangent? So that's not a rule we know. Like, we know that derivative of tangent is secant squared, but what's the antiderivative of tangent? And that's a common thing I see on these problems is students, like, they see the antiderivative of tangent, or they see the integral of tangent, and they say that's secant squared. But no, secant squared is the derivative, not the antiderivative. So the reason we need to use u substitution is because we don't have a rule for this, but I can rewrite tangent using trig rules that I know. Tangent is the same thing as sine over cosine. And when you have sine and cosine in the same problem, one of those is the derivative of each other. The derivative of cosine is negative sine. The derivative of sine is cosine. So we do have something where we can find the derivative of it and say, okay, well, u is equal to this because the derivative is either sine or cosine, and that's being multiplied. But the important thing here is that du needs to be something that's multiplied. So for example, if I choose u equals sine, because that's usually how students will see this, is just like automatically like, okay, u is equal to sine. Because what's the derivative of u? It's cosine. But here's the thing, we're not being multiplied by cosine, we're dividing by cosine. So there's no way for me to divide by du, and this is not cosine times dx, right? This is dx divided by cosine. The dx is in the numerator, the cosine's in the denominator. That is not the same thing as cosine x times dx. So I tried u equals sine. That doesn't work because I'm not allowed to divide by the derivative. It has to be something being multiplied. So let's try again. Let's try u equals cosine x. Then derivative of cosine is negative sine x dx. Now I don't have a negative, but again, we can deal with constants easily enough. Constants aren't a big deal. But I am being multiplied by sine and I'm being multiplied by dx. So this works because we're not dividing by sine, we're multiplying by sine. It's in our numerator, so we're okay here to let u equal cosine. But we would not be okay to use u equals sine. In order to turn this into a positive sine x dx, I just need to divide by -1. So negative du is equal to sine x dx. So I have sine x dx, so my circled part is going to be replaced by negative du. And then my cosine, which I'm dividing by, is going to be replaced by just a u. And then I'm not allowed to leave my bounds in terms of x. My bound of pi and 3 pi over 4, that does not work. I'm going to have to turn those in terms of u as well. But again, all you have to do is plug them into your u equation. So if I plug 3 pi over 4 into cosine of 3 pi over 4, think about the unit circle, 3/4 is going to be right here. That's going to be negative root 2 over 2. And then if I plug in pi, cosine of pi is -1. So this is the integral from negative root 2 over 2 to -1 of negative u to the -1 du. And then the antiderivative of negative, oh, I actually don't know why I rewrote it like that. The antiderivative of negative u to the -1 is not going to use the power rule, because if you added 1, you would get u to the 0. That's not the antiderivative of u to the -1. The antiderivative of u to the -1 is ln of absolute value of u. And there's a negative here because I had a negative here. So I have negative ln absolute value of u from negative root 2 over 2 to -1. And then that gives me, when I plug in -1, absolute value of -1 is 1. So negative ln of 1 minus negative ln of root 2 over 2, because the absolute values make those negatives positives. I want to point out here that you are expected to know, because like if this was a multiple choice problem, there's no way they would leave their answer like this. ln of 1, you should recognize, is 0. So ln of root 2 over 2, they might write the answer like this. Or using properties of logs, just to review with you, ln of root 2 over 2 is the same thing as ln of root 2 minus ln of 2. This can also be rewritten because the square root of 2 is 2 to the 1/2, and using the power rule for logs, that's 1/2 ln of 2 minus ln of 2. Half of ln of 2, so if you have half of something and you subtract a full thing, you get negative 1/2 ln 2. So I'm just showing you like all the, like if this was a free response problem, I would totally be fine with this as an answer. You could just leave your answer like that. But I just want to point out that on a multiple choice problem, you should recognize that that is the same answer as this, which is the same answer as this, which is the same answer as this, which is the same answer as this, all of these are the same answers. So just know that on the multiple choice part, sometimes they simplify their logs in different ways. But again, on a free response, I'm fine with this answer. But you should know ln of 1 is 0 for sure. Okay, and then on this last problem, I have ln of 5x over 3x. So I see a 5x and a 3x. The derivative of 3x is 3. The derivative of 5x is 5. That's not super helpful. So I'm pretty sure u is equal to ln of 5x. So let's see if that helps me. Derivative of ln of 5x would be, using chain rule, 5 times the derivative of ln of something is 1 over that thing. So I get 1 over x dx. Okay, well, I have a 3 here, but that's okay. I still have an over x, right? So I'm dividing by x, so that part's going to be covered, and I'm multiplying by dx, so that part's going to be covered. So I have the integral of, instead of ln of 5x, it's just going to be u over 3, and then the x and dx is being replaced by du. I also need to replace my bounds. So if I plug in 0.2, that's ln of 5 times 1/5 is ln of 1, which is 0. Right? 5 times 0.2 is 1, ln of 1 is 0. If I plug in 2, that would just be ln of 10, so nothing exciting about that. Antiderivative of 1/3 u would be 1/3 times 1/2 u to the second power. And then when I plug in the numbers, I get 1/6 ln squared of 10 minus 0, so just 0. So I just get 1/6 ln squared of 10. Okay, so look through this, make sure you understood those examples. And yeah, that's it for u substitution. So here I have an x, I have a square root of x squared plus 1, and I have to think, okay, what derivative? And I also have a square root function, so I kind of have 3 things again here. I have an x, I have a square root, and I have x squared plus 1. So what thing do I see where its derivative is being multiplied? So the derivative of x is 1, so that's not super helpful. The derivative of x squared plus 1 is 2x. And hey, I do have an x here. That is being multiplied. Again, it's not divided. You always want to have its derivative being multiplied. In other words, it can't be in the denominator. It has to be in the numerator. So the derivative of x squared plus 1 is 2x. And I can turn a 2x into an x. That's not a problem. So I'm going to let u equal x squared plus 1 and see where that leads me. Again, if I pick the wrong u, I can just go back and try something else. So that means du is equal to 2x dx. This is only an x dx, so let's go ahead and divide by 2 so that I just have an x dx. So now I can replace the x dx with 1/2 du. So 1/2 and then du. And then I still have this 2 in the denominator here. So I'm going to have to leave that 2 in my denominator. And then I have the square root of x squared plus 1. And again, x squared plus 1 was u, so the square root of u. Now here's the thing. This is not an indefinite integral. This is a definite integral. So what that means is that I also need to change my bounds. I am going from 0 to 1 if I'm on the xy plane. But I have now turned myself into, or I've not turned myself into, I've turned this problem into a problem in terms of u, which means I'm not on the xy plane anymore. I'm on like the uy plane. I'm in terms of u. So what I'm going to have to do is rewrite my bounds also in terms of u. So it's pretty easy. All you have to do is take your u equation and plug in your bounds. So like u of 1 is equal to 1 squared plus 1 is 2. So we're just plugging 1 in x to get a u out of that. And then u of 0, if I plug in 0, I get 0 squared plus 1, which is 1. So you're just plugging in 1 and you're just plugging in the bounds as your x in your u equals equation. So you're going back to that equation and plugging in your values. So I get 1 and 2 instead of 0 and 1. based on that relationship. So you do need to turn your bounds in terms of u. And then I can solve. And what's fun is that I can just solve this all in terms of u. I don't have to turn this back into terms of x. So the antiderivative of 1/2, I'm actually going to rewrite this. This is the integral from 1 to 2 of 1/4 u to the negative 1/2 du. So the antiderivative of u to the negative 1/2 would be u to the positive 1/2 times 1/4 divided by 1/2. So 1/4 times 2 is 1/2. Just want to double check that. So if I take the derivative, I would be subtracting 1, which would give me u to the negative 1/2, and then 1/2 times 1/2 is 1/4. So that checks out. And because it's definite, I don't have to write plus c, I can just use my bounds. So find the antiderivative in terms of u, and then because our bounds are in terms of u, I can just plug in the bounds. I don't need to turn this back in terms of x. So that's going to be u to the 1/2 is the square root of u, which is 2 in this case, over 2. Minus, if you plug in 1, you would have the square root of 1, which is 1 over 2. So that's my answer. Again, if you have a definite integral, you do not need to rewrite in terms of x. As soon as I wrote it in terms of u, I made sure my bounds were also in terms of u, and then just solve all in terms of u. Don't go back to any x's.